Welcome to Algebra 2. Today we've got section 6.7, modeling with exponential and logarithmic functions. Now, our textbook has been set up in such a way that we've seen a lot of these concepts coming up as we've talked about other types of functions. So we're going to be extrapolating that, kind of including our regression idea and some of the other work that we've done, now expanding that now that we know exponential and logarithmic functions. The first type, finding an equation for an exponential function if we just know a couple of points on the graph. Well, how we make that work is we use this parent exponential function, y equals a times b to the x. And then if we know x and y, a couple of ordered pairs, we can set up a little mini system of equations and then use substitution to find the a and b values for our desired output, our desired equation. Now, to use our calculator, again, this is a lot of recycled material here. You can see that we've done this same work for linear, quadratic, cubic, and quartic regressions. We found those in our stat menu, but they also handle exponential and logarithmic regressions as well. So same type of setup. We can use our stat plot in the calculator to plot the points and see if they follow a trend that shows exponential growth or decay, or if it's a logarithmic curve, just kind of looking at the dots, how are they situated? And if we can't tell between exponential and logarithmic, look for the asymptote. If it's a vertical asymptote, it's going to be logarithmic. If it's a horizontal asymptote, we can bet that it's exponential. Okay, once we have that, we know if it's going to be exponential or logarithmic, then we have these data points entered in list 1 and list 2. Remember, that's the stat button and then edit. And then we'll go into stat, calculate, and then we'll choose either expreg or natural log regression to get our regression equation out of it. And just, I should say, before I move on, that these regression equations, they're going to be a best fit curve. It's not going to be an exact equation, but it will approximate the points using not a best fit line, but a best fit exponential equation or a best fit natural log. All right, so our first task, we have a couple points. We need to find an exponential function that passes through those points. Remember, this is going to be based off of our parent exponential function, y equals a times b to the x power. All right, so for number 8, my x and y that I'm given are 2, 24. That means the y value of 24 equals some a value times some b value to the x power. In this case, x is 2. And the other point tells me that 144 equals a times b to the third. Again, just plugging in the x and the y. And now we've got our system. We don't know a, we don't know b, but we've got 2 different equations, so we can use the substitution method. So working in the first equation, I'm going to divide both sides by b squared to find that a equals 24 over b squared. And then we'll substitute that into the other equation. Now 144 equals 24 divided by b squared times b cubed. And, hey, look at this. I'm dividing away b squared. That will cancel out 2 of those 3 b's that are in the b cubed. And I get 144 equals 24b. Divide both sides by 24. And we find that 6 equals b. All right, now I could plug that into either of the 2 equations up above. I'm going to choose the one that we had underlined earlier. 24 equals a times b squared. That's 6 squared, or 36. And if we finish solving for a equals 24 divided by 36, which simplifies to 2/3. So the equation, y equals 2/3 times 6 to the x power. Okay, and just to check to make sure that's working, I would plug in both of those points and just make sure they make true statements when we plug in the x and the y that we were given for each of those points. Now for number 14. This one, obviously we have some bigger numbers, we have some decimals, so we're going to be relying on a calculator to help us out a little bit, but it's still the same process. So here, 6.4 equals a times b to the second, and 409.6 equals a times b to the fifth. Again, I'm going to be working with this first equation. Solve that one for a so we can use the substitution method. A equals 6.4 over b squared. Substitute that in. 409.6 equals 6.4 over b squared times b to the fifth. And here we've got the same thing. B squared is going to be canceled out by that b to the fifth. It will reduce it to a b to the third power. Not surprisingly, properties of exponents show up in exponential equations. We've seen that happen. So let's see, 409.6 equals 6.4b cubed. We'll divide away the 6.4. That's 64 equals b cubed. And to solve for b, just like in chapter 5, we will take the nth root, in this case the third root of both sides, and find that b equals 4. Plug that back in. So my a value is going to be 6.4 over 16, and I find that a equals 0.4. So we get y equals 0.4 times 4 to the x power. Let's just check that in a calculator really quickly. If I take 0.4 times 4 to the second, I get 6.4. And if I take 0.4 times 4 to the fifth, I get 409.6. So our exponential equation that we came up with contains both those points that we started with. So pretty easy check to type those into a calculator. Okay, example 2, use a calculator to find an exponential function. Let me pull up the calculator for you. Now they do say exponential, so we don't have to go through and plot these points and see what type of function they model. And we can go ahead and enter in our x values and y values in list 1 and list 2. So I'm going to hit the stat key and then edit. Under list 1, I'll type in my x values. So we've got -20, -13, -6, 1, 8, and 15. Then in list 2, here go the y values, 25, 19, 14, 11, 8, and 6. And just make sure that all my x's and y's are typed in the right way and they all match up. I don't have one list that's longer than the others. Okay, so we type that in, then it's the stat key. It saved all those points we entered. We're going to go over to the calculate menu, and we want to scroll down until we get to EXP reg, exponential regression. So we'll hit enter there, hit enter to run the regression, and there you can see we've got 11.1357 times 0.96 to the x. And that would be our regression equation. So here I'm just going to grab that. So how we interpret that calculator screen is as follows. Our function is y equals 11.136 times 0.96 to the x power. Now, obviously, this doesn't look very clean with our multiplication. So a cleaner way to write that would be y equals 11.136 times 0.96 to the x, using parentheses and 0 point to show the decimal point a little bit more clear. We don't want to lose any of that as we write our function. So that is the preferred method to write that down below. All right, and our last example, believe it or not, here we've got the f-stops on a camera, control how much light enters the camera. Okay, let S be the measure of the amount of light that strikes the film, and F be the measure on the f-stop. We've got a table here that shows several f-stops, and then the S value that goes with them. And we want to find a logarithmic model, so S equals A plus B natural log of F. Okay, so I know that F is the input into the logarithm, and S is going to be the output of the entire function. All right, let's bring up our calculator, clear out what we have, and enter in that information. So I'm going to edit my lists again. And if you hit the up arrow key, so it has L1 selected, you can hit clear and then enter, and it will clear out the entire list. Often that's a lot faster, and it's nice to know that we've cleared out everything. There's no lingering values from our other examples. All right, so list one, our inputs, those are the f-stop values. I've got 1.414. I've got 2, 2.828, 4, and 11.314. Then the outputs of the whole function are 1, 2, 3, 4, and 7. All right, so now we're going to find that logarithmic function. It uses natural log. So I'm going to go back into stat, calculate, and we're going to toggle down until we get to natural log regression. Hit enter, and there we have our function. Now we do have some scientific notation there, so we want to be careful about that. So again, I'm going to grab this off the calculator. And then we'll work with it because our question's not just to come up with the exponential function, right? Now we have to do something with that. So it's not like example 2, we're going to use our function. All right. So the function we arrived at is y equals 3.980 times e to the negative fourth. That is scientific notation. So that means it is a tiny, tiny number. This decimal point is moving 1, 2, 3, 4 places to the left. So 0.000398, okay? And then plus 2.885 times the natural log of x. Okay, so we're following the format that they wanted, and I used y's and x's, but really it should be S equals that function with F as an input. And then it says to estimate the amount of light that strikes the film when F is 5.657. So we're anticipating, based on the table, something that's going to be between 4 and 7 as an output, and probably much closer to the 4 than to the 7. So in the calculator, yet again, I'm just going to type in 0.000398 plus 2.885 times the natural log of 5.657. And the answer I get is S equals 4.99979. So we could say S is approximately 5 when F is 5.657. So we came up with our regression equation, and then we used that equation to make an approximation based on an input that wasn't given in our table. And again, that's very similar to what we've used calculator regression for in the past. All right, that does it for the lesson here. Very quick one. And you can see the assignment is short as a result of that. We've only got a few problems here. 7, 11, and 15 are using that substitution method. 19, 21, 23, and 33, those are all using calculator regression to answer those questions. But that does it for section 6.7 here in Algebra 2.